this video I'm going to go from where we started last time with naive Bayes and deriving the maths and showing how to work an example through by hand, to actually now showing how to code it up. So as you can see here, this is a sort of central statement. We want to work out for every hypothesis the probability of that hypothesis given the evidence that we've got. And we can turn that around using naive Bayes formula, and we can estimate that using this on the right here. So the probability that the first piece of evidence is equal to a specific value given the hypothesis times all the others, okay, times the probability that the hypothesis is equal to a specific value. And what's on the bottom doesn't matter too much because it will be the same for each one. It does not depend upon the hypothesis, therefore if we just want this to pick, then all we really need to do is calculate the top part of this fraction here, and we can use that as a score. So we're going to look at now how to do that with R to actually program up an example. So first thing I've got is well, we'll just load up a data frame, so we've got something to look at, and then we can maybe have a look at how we might go, how we might go about it by considering a few R functions, and then we'll actually I'll show you the code to actually do it. So this head lens here. Right, so this is the data we're going to look at. I have written the program generally, so it should pick up any data frame. At the moment it's got to be categorical. I will look at continuous variables later on, but provided it's categorical variables, I think this code should work. Just one word of warning: if you do pick it up and try and use it, I have imported as.is equals true. Means it's not going to change all of these effectively string variables here, because I put them as strings, and I will change them to factors. Just the way it works. I think it probably is a way of coding it doing that. I've not done that. Okay, it might not be the best practice, but that's the way I've got this algorithm to work. Okay, it was just easier, to be honest. So first thing we're going to look at is we want to try and look at what probability things we want to generate here. So what are the equivalents? Now we look at this data frame. Let's just try and think. What is this? How do we think about this general statement given this specific example here? Well, the first thing is we want to have the probability of something. But what is that? It's going to be, well, age is effectively like my capital E1 here. I want to find out the probability of age being equal to young given recommended underscore lenses equal to none, say. Okay, as an example. So that's effectively just like one of these statements here. Probability of the evidence given the hypothesis. So we've got it the right way around. You can see here. These are the things we're trying to predict. So that's effectively like my hypothesis. And age being equal to, pop that in, young is as an example of that. So we want to, okay, that's what we're going to try and do, and we have to do that for every single hypothesis and for every single feature, effectively, and for every single item within that feature. So we need to do this for the age feature, we need to do it for young, we need to do it for the other values that age could take as well. Okay, so one function that's very useful, you might be thinking, or if you've done some R, you might already know, and I'm going to just put this in a variable as well, so we can build things up a little bit. The table function helps us a lot here, and we're going to do lens $age comma lens recommended lenses, and we'll see what we get. So we've done that. Tab. Okay, good. So what's this table telling us? Well, effectively, of all the hard lenses, you can see, yeah, that those are all the hard lenses. One is pre-biopic, whatever that means. One is pre-biopic, and two are young. So we wanted to work out, given the hypothesis is equal to hard, yeah. Go back to what you were thinking about before. What's the probability that we're in fact young? Say it's going to be 2 all over 4. Similarly, if we want to work out this biopic, it would just be 1 over 4. So the first thing we probably want to do, okay, is to add up these. So we want to try and get to these conditional probabilities. Well, we're going to need to add up these columns, okay, and we can use the apply function to do that. So let's just a variable I've called all. It's going to be apply, and we're going to look at that, apply it to the table. The 2, so we're applying it to the variable table which created. The 2 means we're doing this over the columns, okay. It would be if you wanted to put 1 in there you would add up the rows, but we want the columns, so we're going to add up all of the columns, and all in here now will just be 4, 15, 5. Okay, so yeah, that's we've added that up. So the next thing we need to do is to say, well, I actually want to divide each of those by 4, each of those by 15, and each of those by 5, because that will give me the conditional probabilities that I want. And then I need to, and you can see what next thing I'm going to have to do is going to have to loop over it. And then when we look at the program, what the program will actually do is loop over every feature. We've done this for one feature here. So let's just, there's another useful function that's sweep. Again, still want to do it for the same table, this table here. We still want to do it over columns. We now want to use the all vector we've just created, and we want to do division. Alright, I'll just run this, and then you can sort of see what it's doing. And it's basically applying, it's doing division, and it's doing division of what's in table by what's in all, but it's picking the first column in table, it's doing 1 divided by the 4, and then it's doing 1 again divided by 4, so you can see 0.25, 0.25. Then finally 2 divided by the 4 will give us 0.5. Then similarly 5 over 15 is giving us a third, 6 over etc. Okay, so that's where we've got to with that. Next thing to do, and finally soft, yeah, I mean, it's the same thing. Yeah, I'm not going to explain that actually. So that's how we can get the conditional probabilities. And what will we need to do next? Well, we need to get all of these for every single feature. So the way program now, let's actually put a breakpoint in the program, fire up the program. Okay, I need to source it again so the breakpoint becomes live, and there it is. Run the program, and off it goes. Yeah, we get to that point there. We've got the number of features. Let's so let's just go through the code line by line. I think it's pretty clear what this is. This is the number of columns in my data frame. The data frame I pass to the naive Bayes function I've got here. You can see I'm passing lenses, lens data frame to this function. So this data frame here is that. And the number of columns, if you go next, we then look at number of features. Well, that's going to be 4, because all it's doing is taking the number of columns in the data frame and taking off 1. And it makes sense to do that because they're all features apart from the last thing which we're actually trying to predict. So, whoops. Yeah, I didn't want to do that, did I? Num underscore. Let's go back. Features. Hit return there. You get 4. Okay. Let's step again. Number of observations. Nu underscore obs. 24, because there's 24 rows in that's all that is. Okay, so we choose the n col and the n row there to work that out. Let's just step again. Num underscore cl. Number of classes is 3, and what that's done, it's picked up the unique members of the last. So this is the data frame. Okay, I'm saying I want to look at the last column. That's the number of features plus 1. So that's going to take us through all the features, and then plus 1 take us to the thing we're trying to predict. I want to know how many of them are unique. Okay, so it's just whittle that down, and then it's just the unique ones. So rather than have all of them, it will just pick the unique ones and just put them in a list, and then or a vector. And then after that, length here is just finding out how long that is, and that gives us 3. So we found out we've got 3 unique things there. Okay, so the next thing we want to do is to basically, as I was just saying, we want to loop over the features, and we want to create a table for each one. So let's step into this loop and see what happens. So the first thing we get is the table. Now it's going to be the same table we looked at just a minute ago. So if we just look at tab there, okay, 1, 2, 2, 4. So it's done exactly what we saw before. But now, of course, it's doing it because I've put in a general data frame. It's doing it, for the data frame we've got. This plus lambda, I've set it to 0. It's actually a smoothing idea. Now, smoothing is very useful. It stops problems that you can have with 0 probabilities. I've got it set to 0 here, so it actually has no effect at all. I might talk a little bit more about smoothing in a later video, but I'm not going to talk about it today. Okay, so the first thing we're going to look at here, we've got I is 1, so yeah, we've done that first bit. Let's step again and see what these different things do. So all, as you can probably, because it's very much like what we just did before now, all is going to sum over the columns, and you can see that really, data frame here, I'm just doing this generally now. It's the same data frame, but what am I doing? I'm looping over all the features. So I've worked out what the features are. I'm looping over them. I'm tabulating them with whatever is in the last column that is effectively where my where the things I'm trying to predict are. Yeah, so it's the same idea. I've got data frame here. I'm just going over the number of features. I'm just doing it fully programmatically now. So you could put a different data frame in if you wanted, and it should all still work. And the first thing I've done is I've worked out the all. Next thing I'm going to do is probably and I've done that. So I've got now that conditional probabilities. Let's just do that. It should now show us a matrix where we've got the conditional probabilities here down the side there. Okay, so let's step through that again. And we're doing the same thing now. We don't need to keep working out this all every time, because it's just all of the hards, all of the softs, all of the nons. That will be the same each time. We've reworked out tab now for the next feature. So if we look at tab now, it should be for whatever the next feature is. Let's just knock that off. Yeah, because we did this, we stepped onto the features, and then we're now on to the next feature. And we've got a similar table as before. And we can step through. We will do the same sweep. Okay, you can see you've still got 4, you've still got 15, you've still got 5, so you don't need to recalculate all every single time. That's why it was one to start off the comprobs. I need to update it each time, so it's useful just to set these things up with I is equal to 1 here. Just the first time you go around, work out the all once, start off the conditional probability with the first one. Then after you do that, you're going to have to, because I want to have a big conditional probability matrix, so this next thing here, it's worked out the conditional probabilities for the next one. It's then binding those using the R-bind, and you'll see it now if I just step again. So okay, if we look at comprob now, it's not only got the ones it had before, it's got the next ones down as well. So okay, and we can keep going like that, and we'll get a full list of all the conditional probabilities. Now the next thing I've done at the end here, so let's just see if we can it's not going to, okay, I'm going to have to step right the way through, that's fine. So we'll just go through and it will do the others. There's only 4 of them, so it's no big deal, just step through. Okay, let's stop just there. So now I should have in comprob, we look at that. Yeah, I've got all of them now, so you can see we've got, that was the first feature there, that could have 3 different values. Second feature could have those 2. I believe that the yes and no was another feature, and finally normal and reduced was the final feature. So you've got all 4 features in there. I've just also done all, and I'm going to add that to my conditional probability table. It's not technically a conditional probability, but it's just programmatic convenient to do it this way, because okay, let's just have all, thank you. Yeah, so all is just the probability of being hard, probability of being soft, probability of being non, probability of being soft. So effectively that's just 4 over 24, because we know that there are 4 that are hard. So there you go, you can see that, that's just that bit there, and I'm going to append that, so it's not a conditional probability, it's just programmatically useful to stick it at the end of my conditional probability matrix. And then we step on to the next bit. So now I'm going to go over all the observations, and I'm just going to basically use the probabilities that I've used the conditional probabilities and predict what it would give us using the naive Bayes algorithm, rather than using the naive Bayes algorithm and the conditional probabilities I've got. And all I really need to do that is I'm going to go over every single observation. That's just because I'm making a prediction for each observation in the data set. I'm going to step to the next bit, and we see obs there. So that's just picking out the conditional here. What we're doing here is we're taking, you see, I'm going from the first to the number of features, so that will be 4 there. I'm going for this particular observation, converting it to a character, and I'm also adding the all onto that character, and then I'm picking out the conditional probabilities for each of those. So I'll get the conditional probabilities for those features. Okay, it's effectively picking out, if I go back to the theory bit here, it's picking out all of these, okay, and this, the all bit's effectively that bit at the end, yeah? Okay, and it's doing it for a particular example now. So if we go back to the next, okay, so what do I want to do now? I want to multiply them all together. So now we do the apply again, we apply it to obs, we do it down the columns, and we multiply them all together. Okay, so if we look at obs, let's have a look. Yep, so we've got hard, we want to work out the want to multiply all of those together. So I'm going to get basically the estimate for hard, the estimate for non, and the estimate for soft. So when they're all multiplied together, I'm effectively estimating this. So let's just step over that. Step I equals 1, it gives me a prediction. It does the same thing again, and preds now is just going to pick the maximum. Okay, so I've started that with I is equal to 1 because I need the first one, then after that I'm just going to append the remaining predictions to that. So that's all the I equals 1, just initial to start it up, and then after that I'm just going to append the remaining predictions. You see this here is effectively the same as this there. Okay, so we can go around again and we can do all of that, and it's doing the same thing for each one. And we can stop it here and just have a quick look at what obs is equal to now. Obs. Okay, and yeah, so we've picked up the ith row from the data frame. We've worked out, and what did we get for that? We got young, myope, yes, reduced, all. Well, all wasn't that particular example, but if you look at the ith row in the data frame, it's just worth doing this, I think. If I pull that out, what I should see here copy, paste. I've not gone too far. I think I might have got something I didn't want there. Probably the extra bracket. Yeah, I think that should now work. We've got young is the third row. We've got young, myope, yes, reduced. Young, myope, yes, reduced. Conditional probabilities for each of those have been pulled out of the conditional probability matrix we set up earlier on. And then we have all, right? And then we're going to predict which is best by multiplying them all together. Yeah, and you see how these, I was talking about the smoothing a little bit earlier on, you can see how these zeros are a little bit problematic really, because this is guaranteed to be 0. Yeah, and you can get around that because you might not really want that. It doesn't actually work too badly here, but if you don't want to zero your probabilities, you can effectively use this smoothing idea. And that was what the lambda there was for. It's effectively increases, it increases everything by 1 or by lambda, which will still maintain that, it'll still be a valid probability model at the end of the day. They won't quite be the right probabilities, but you'll stop having the problem with 0 probabilities and the fact that this will now, whatever else happens, however big this is, this will be 0 because of the 0 you had here. So it can be a useful thing to do. Okay, but we'll leave that for today. Okay, so we got as far as we can see. That's, yeah, so we see how this now, the third row of the data frame is picking up the conditional probabilities for each one. It's going to multiply them together. It will, let's just step again, and I think we might go to the fourth now, but never mind. So we multiply the probabilities together. Let's just have a look at those. Just obs, oops, prob. Yep, and you can see what we get there for those are for them. And let's just see what the obs was for that. So that's multiplied all those, do all that lot together. That's multiplied all that lot together, multiplied all that lot together. And you see we had a 0 in there, so that one effectively came to 0. Yeah, you might not, as I say, it's although, yeah, well, that one came to 0 there, yeah. Right. Yeah, it's interesting we've got some conditional probabilities of 1 here as well. I expect that's because for the hard they were all yes, and for the soft none of them. Yeah, okay, so yeah, so for the hard, given that they were hard, the probability of being yes is 1 because every single hard was 1. Okay, just got halfway through that and I have to stop. Never mind. Hello. Yep, do you want me to come outside so you can see where we are? Okay, sorry for that interruption, just finish things off. I think we saw how the model was working, how the predictions were being made, how the conditional probabilities were being calculated and then used. At the end of the code here I've just got a line that basically looked at the error that's made, so that's it's summing up where the predictions are equal to the values in the data frame, and then it's outputting an error. The model here is just then outputting a list of conditional probabilities with the data frame values, the predictions that we got, and with the error. So we look across, and this is that now. I've run the algorithm to the end since I was last recording. And if you look at the prediction lengths here, you can see first one is basically conditional probabilities. Then after that we've got the predictions from the model, the actual data, then the predictions from the model after that, and they're at the end. So we've got a 4.16667% error, so that basically means we've got one wrong. If you look across, most of them have been predicted correctly, but I think there is one wrong somewhere. Yeah, if we look there, so that none there matches the so none from the data, none that we predicted, soft from the data, soft that we predicted. You can see just a little way along here we've got a none that was in the data and a soft we predicted, so it didn't work entirely perfectly, but you can see on the training test at least it did have a reasonably good error. Yeah, so that's that brings us to the end of the way my algorithm works. I'm gonna do some more videos on naive Bayes. I'm going to sort of I did this in the past. I had a look at how well. We just go back. That's my presentation. Just have a little look back. Fully E1071 is I think it's basically the sort of one that the R package uses. If you use the caret package to do prediction in R and you load up naive Bayes, I think this is what this algorithm uses. I know in the past I've run this and I've had a look at how well it works against mine. It pretty much does exactly the same thing, so I might have a quick look at that in a next video. I'm also going to show the theory, because so far we've just looked at categorical variables. It's perfectly possible to do naive Bayes for continuous variables as well. We want to sort of use the normal distribution effectively. It assumes the variables that are continuous are normally distributed, and uses the normal distribution PDF, the probability density function for that normal distribution. So if you want to sort of have a look at my normal distribution video, that could be a sort of precursor to that. As I say, we'll be doing continuous variables in a later video. Okay, thanks for watching.